Okay. I think for today I will finish off all the polar. Last time we did the rows. Um, we have sine, we have cosine. I think to make a note, additional notes for sine and cosine who are in odd number for the angle. You will see they have certain patterns. Okay. For sine, you have the first one is up here. The second one is going down, and the third one is going up. Okay. And for the cosine, however, it will start always on the right. Okay. How to say that? One of these four angles. Okay. It will have this at least for the cosine. Okay. Always having that for odd number. And for the even number, if you have sine, you will have the first pattern is like x like that. And for cosine, you will have like a plus. Okay. Okay. The angle. Okay. That's just some additional notes. Okay. But if you are confused and maybe doesn't remember how to all the patterns, what you need to do is you define the angle and you get the angle between all the curves, all the petals is 90. And then you can start by uh, drawing. Like for example, the first one you can draw here, and then second one here, and go here. Actually, it's like this pattern. Uh, like this one, the 2 cosine 3 theta. Maybe you can start from here, or maybe from here, because 0 is 1, right? So from here, going here, going here, going here, and it has certain special patterns. If you check the angle with the value. Okay. Hmm? Really? Can you hear me, actually? Hey, Akili, can you hear me? Okay, can you hear me? Hello. Can you hear me now? Okay. Well, I think we can continue now. Um, the same goes for this cos phi theta. So you go here, go here. I think we go here first, and then go here, and then this is the last part. Okay. And all the pattern, they will have that special movement. But in case uh, you want to confirm whether it's correct or no, then you can do the checking the at least the maximum point and the zero. Check the zero and the maximum point in each every angle possible. Okay. Okay. Now the next part is we call this is the plane curves and parametric equations. Okay. If f and g define on interval, let's say some interval I, then ft and gt is a plane curve in which the x is ft, dy is gt. T is element of the interval, is called parametric. Parametric equations with t as parameter. I think this introduction for parametric, uh, I believe you already have some um, some brief applications in physics. I think, especially if you have uh, x y axis and you have time, like when you are moving, maybe it like someone running and then it's jumping and then it changed in x and y and also in t. Okay. Let me show you how it works. Okay. So example is x t squared minus 3t and y is t minus 1. So we are considering x and y is our positions, okay, and t is time. Okay, as t increasing from 0 to some other t, we can see x and y changing, right? So we have wait. Okay, while we are waiting, I'll give you some notes for the polar curves. Okay, this is called the lemniscate. Okay. It's easy to draw compared with the others. The lemniscate is r squared equal a squared cosine 2 theta. And how to draw? For the cosine, you will have like this, and it's just saying that this is the a, the distance. Okay. The a. For example, if you have 9 cosine 2 theta, you just have, what you need to do is just this 3, 3, and draw like infinite symbols. And then the other part is sine. Okay, r squared a squared sine 2 theta, and this drawing is like this. Okay. And the a, for example, if you have 4 sine 2 theta, the a is the maximum value of this angle. Okay. Like you have 1 circle, 2 circle, meaning you have 1 point, 2 points, so 2 unit circle. Okay. And for if you have 3, so 1, 2, 3, 3 unit circle. So it should be symmetry. So yeah, symmetry. Okay. And then yeah, I think that's all. That's all for the lemniscates. Okay. Okay. So parabola. The first one is a parabola, and then distance. This is just additional notes. Okay, distance. Circle, also additional notes. And this the second actually is the ellipse. Okay, you can say if a greater than b, the major axis in x. If b greater than a, it's not 0, it's a. Should be in the y-axis, the major. And yeah, this is the if b is greater. And the other one, um, this is we call the hyperbola. Okay, so it's the same as ellipse, similar, but instead of plus, we have minus here. Okay, the minus can be y, or it can be switch. Okay, and it will be switch. Okay, so the hyperbola from top and down. This is left right. If this is minus, positive minus. Okay, so you have this and this, left right. If you have y minus x, it's up and down. And the center, HK, is the center of the asymptote. So this red line here is the asymptote. Okay? And A and B is the distance from the center to the vertex. Okay? For the vertex here. And to draw this, actually, to draw this in a short time, you pick up the center, okay? Pick the center, make some line. If you don't know the asymptote, then that's fine. Just make some line here. Makes the hyperbola left and right, and at the very end, it's nearly touch the asymptote. And then make a box here. Make a box here, and from this box, this will be B. This will be A. Okay. In case you are just roughly sketching, that's roughly sketching, really not in details. Okay, roughly sketching. That's how you dealing with the hyperbola. The other one is the other form. It's y minus x. So it's here, up here. And now A is here, B is here. Okay, it's the distance from vertex to center and center to this box. Okay, now the question is, why all of this hyperbola, ellipse, parabola, it's called conic sections. Did you know conic? Yeah, you can imagine it's from cone. Okay, you know cone, like in your ice cream, right? So let me draw cone. Okay, and actually cone, the full shape. If you're in math world, you say cone, you need to draw the whole cone. This is the whole cone. Okay. And all the conic sections, it came from the cone. So if you slice this, it becomes a circle here. If you slice but a little bit, giving some angle here, not really straight, it's giving you ellipse. If you try, if you slice, cutting here, it will be giving hyperbola, right? And parabola is just a tip on here, maybe here is becoming like that. A parabola. Let's see here. Yeah, here, this, and cutting here. This slice become parabola. This slice from here, is hyperbola. This is circle, ellipse. And this is actually If you want to draw correctly according to definition of a parabola, so we have P point here and D. Okay, this D is called directrix. It's always in the front of the parabola. Okay, and you have focus here at the behind of the parabola. Okay, and the relations between all of this line, you can find it through some triangle. So if P is any point in x y axis on parabola, then the distance from P to the focus, okay, so P can be anywhere. Okay, P can be here, 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 and PF is always x squared plus y minus p squared. This is from the distance. That's why I mentioned the distance at the very beginning. So this is from the distance nodes. Okay, so we have this property. So this is why it's called parabola, because the distance from the any point in parabola to through its focus is equal the square root of x squared plus y minus p squared. And we have also PD. It's the line or the distance between any point P to the line or the we call D is directrix. Okay, it may seems not really useful, but in order to draw, sometimes you need to know the directrix. Okay, the directrix line. Okay, so parabola, based on the conic sections definitions, is the distance PF equal PD. That's parabola. That's parabola. Okay. If we solve this, try to find the form, we get the form, this form. It's parabola, right? Y is having x squared. Okay. And depends on P, you can have open up parabola or down. Okay. So that's parabola. So the definition is actually the distance from any point on parabola to focus is the same as that point to its directrix. So directrix is basically, the definition is any line, then when you put here, it's equal. Okay. Do we have example? Okay. A little bit example. If you have find equation of parabola with vertex is 0, 0, focus is 0, 2. So because directrix is always mirror the focus, like PFPD, right? So if you have 2, focus 2, then directrix will be -2. And we can put in the equations. So the equations in conic section for parabola is x squared 4p, okay, 4py. That's the default set for conic sections for parabola. And we just put in the focus, and this is the equations. And to draw, we are setting up directrix. Maybe I'm not draw in scale. So it's 2. It should be 2. It should be the same. Okay. So it's -2. It's 2. So this distance should be the same. Okay. And when you go anywhere from this whole parabola, maybe you want to change the point, this distance PF and PD always the same. That's the definition of parabola, the property. So we are seeing in conic sections, rather than seeing some sort of formula for parabola like x squared plus 2x minus something, we are seeing in geometric approach, okay, in more geometrical approach in conic sections. So we deal with the focus, we deal with the directrix, okay, to define our conic section. So most of the, I think all of our conic sections, they will have focus, directrix, and we will define each geometrical shape based on these relations, focus, point, and directrix. So the first one is parabola. Okay. Okay. Any questions? If no, I think we've finished until here. Tomorrow we continue back to parametric. It's a little bit parametric. It should be not too complicated. And then next Tuesday quizzes. Wednesday we are back to the conic section. And also, I think tomorrow half part will be parametric, half will be going back here. It should be not too difficult. Okay, I think that's all for today.